Have you ever wondered what would happen if you crossed the point of no return, the invisible boundary, where even light can never escape? Would you discover another universe? Would time completely stop? Or would you simply disappear from existence forever? For decades, scientists have tried to answer one of the greatest mysteries in the universe. We have photographed black holes, detected the gravitational waves created when they collide, and watched stars orbit around invisible giants. Yet one question remains unanswered. What's really inside a black hole? In this documentary, we're going on a journey unlike anything you've ever imagined. We'll travel from the outer edge of a black hole all the way toward its mysterious center. You'll discover what happens to light, matter, space, and even time itself. We'll separate scientific facts from popular myths, explore the latest theories, and ask one incredible question. Could a black hole actually be a doorway to somewhere else? But before we step inside, we first need to understand what a black hole really is. Imagine you're floating peacefully through deep space. The stars shine in every direction, and everything seems perfectly calm. Suddenly, you notice something strange. The light from distant stars begins to bend. Galaxies appear stretched into glowing rings. Space itself looks distorted, as if reality is being pulled toward an invisible monster. You can't actually see the object causing this effect, because it doesn't emit any light. Instead, it traps every photon that comes too close. That invisible object is a black hole. Contrary to its name, a black hole isn't a hole at all. It's an incredibly dense region of space where gravity has become so powerful that nothing, not even light traveling at nearly 300,000 kilometers per second, can escape once it crosses a certain boundary. But here's the real mystery. How can something become so powerful that it captures light itself? The answer begins with the death of a giant star. Millions of years before a black hole is born, a massive star shines brightly by constantly fusing hydrogen into heavier elements inside its core. This nuclear fusion creates an outward pressure that perfectly balances the star's own gravity. For millions of years, these two forces remain locked in an invisible battle. Gravity tries to crush the star inward. Fusion pushes outward with incredible energy. As long as both forces stay balanced, the star remains stable. But no star can burn forever. Eventually, it runs out of fuel. And the moment that happens, gravity finally wins. In the next part, you'll witness the violent death of a massive star and see how one of the most terrifying objects in the universe is born. If you're excited to continue this journey into one of the greatest cosmic mysteries ever discovered, don't forget to like this video, subscribe to the channel, and turn on notifications, because we're only getting started. As the massive star runs out of fuel, something extraordinary begins to happen. For millions of years, nuclear fusion had acted like an invisible shield, constantly pushing outward against the crushing force of gravity. But now, that shield is gone. With nothing left to resist it, gravity takes complete control. The collapse begins. At first, the outer layers of the star rush inward at incredible speeds. The core becomes hotter, denser, and more compressed every single second. Temperatures rise to billions of degrees, and pressures become so extreme that atoms can no longer survive. Electrons are forced into protons, creating neutrons and releasing an enormous number of tiny particles called neutrinos. In just a few seconds, the star's core transforms into one of the densest objects in the universe. For some stars, this collapse stops here. They become neutron stars, objects so dense that a single teaspoon of their material would weigh billions of tons on Earth. But if the original star is massive enough, even neutron matter cannot withstand gravity forever. The collapse continues. Nothing can stop it now. The core shrinks smaller, and smaller, and smaller. Its density increases beyond anything we can recreate on Earth. Gravity becomes unimaginably powerful, bending the very fabric of space and time around it. Then, something spectacular happens. The outer layers of the dying star explode outward in a gigantic supernova, producing more energy in a few moments than our sun will release during its entire lifetime. For a brief time, the explosion can outshine an entire galaxy. The shockwave races across space, scattering heavy elements like iron, gold, platinum, and uranium into the universe. Every planet, every mountain, every living creature, including every atom in your own body, contains elements that were once forged inside stars like these. In a way, we are all made from the ashes of ancient stars. But while the explosion expands outward, something even stranger is happening at its center. The remaining core keeps collapsing inward. Its gravity grows stronger and stronger until it reaches a point where the escape velocity exceeds the speed of light itself. And because nothing can travel faster than light, nothing, not particles, not radiation, not even light, can escape anymore. At that exact moment, a black hole is born. Interestingly, if you were watching this event from a safe distance, you wouldn't actually see the black hole appear. You would only notice that the brilliant star suddenly vanished, leaving behind a region of complete darkness. Yet the invisible object would continue pulling on nearby stars with incredible force, revealing its presence only through gravity. This is why black holes remained hidden for decades. They don't shine. They don't reflect light. They reveal themselves only by the way they warp the universe around them. But even more mysterious than the black hole itself is the invisible boundary surrounding it. Cross that boundary, and there is no return. In the next part, we'll approach this mysterious border known as the event horizon and discover why it is often called the point of no return, and what an astronaut would actually experience while getting closer to it. Now that the black hole has formed, it's time to move closer. Imagine you're inside a highly advanced spacecraft, slowly approaching one of these invisible cosmic giants. At first, nothing seems unusual. There are no giant teeth, no swirling tunnel waiting to pull you in, and no visible hole floating in space. In fact, if the black hole weren't surrounded by glowing gas, you might fly straight toward it without even realizing it was there. But the universe is already changing around you. As you move closer, the stars behind the black hole begin to bend into strange shapes. Their light curves around the object instead of traveling in straight lines. Entire galaxies appear stretched into bright arcs, while some seem to appear in multiple places at once. This incredible effect is called gravitational lensing. According to Einstein's theory of general relativity, gravity doesn't simply pull objects together. Massive objects actually bend the fabric of space and time itself. Light always follows the shape of space, so when space is curved, light curves with it. You're no longer seeing the universe as it truly is. You're seeing a distorted version of reality. As your spacecraft continues forward, another strange effect begins. Time itself starts behaving differently. Your onboard clock appears perfectly normal to you. Every second feels exactly the same as it always has. Your heartbeat doesn't change. Your breathing remains steady. Nothing inside your spacecraft seems unusual. But for someone watching from far away, something unbelievable is happening. They would see your clock ticking more slowly. Your movements would appear delayed. Every signal you send would take longer and longer to arrive. This phenomenon is known as gravitational time dilation. The stronger the gravitational field becomes, the more slowly time passes compared to distant observers. If your mission lasted only a few hours near an extremely massive black hole, years, or even decades, could pass for people waiting back on Earth. You would return to find an entirely different world. Friends would have grown old, cities would have changed, entire generations might have come and gone. This isn't science fiction. It is a real prediction of Einstein's equations, confirmed many times by experiments using atomic clocks on Earth and satellites orbiting our planet. But the closer you move toward the black hole, the stranger reality becomes. The darkness ahead seems larger than before. Its edge becomes perfectly circular, surrounded by a glowing ring of light created by matter falling inward at incredible speeds. Beyond that dark boundary lies a place from which no message has ever returned. Astronomers call this invisible border the event horizon. Cross it, and every possible path through space and time leads only deeper into the black hole. There is no turning around, no escape, no second chance. The question is, what would actually happen if you decided to cross that boundary? Would you notice the exact moment you entered? Or would the universe have one final surprise waiting for you? Your spacecraft drifts silently toward the event horizon. The glowing ring surrounding the black hole grows brighter with every passing second. Behind you, the universe still looks familiar. Stars sparkle in the distance, galaxies shine across the darkness, and everything seems almost peaceful. Ahead, there is only blackness. According to almost every science fiction movie, this is the moment when you would suddenly be pulled apart or smashed into the black hole. But surprisingly, real physics tells a very different story. If the black hole is extremely massive, millions or even billions of times heavier than our sun, you might not notice anything special at the exact instant you cross the event horizon. There would be no wall, no explosion, no invisible barrier pushing against your spacecraft. Your instruments would continue working. Your heartbeat would remain steady. From your own perspective, crossing the event horizon would feel completely ordinary. But something extraordinary has already happened. Without realizing it, you have crossed the point where escape has become physically impossible. Even if your spacecraft had the most powerful engines ever imagined, they would no longer be enough. The reason is not that gravity is simply pulling harder. The reason is far stranger. Inside the event horizon, space and time begin to exchange roles in a way that challenges human intuition. Outside the black hole, you can freely choose different directions through space, but you cannot stop moving forward through time. Inside the event horizon, moving toward the center becomes as unavoidable as moving toward tomorrow. Just as you cannot decide to travel backward into yesterday, you cannot choose to move away from the center of the black hole. Every possible future leads inward. Every path ends at the same destination. From far away, however, someone watching through a powerful telescope would see something completely different. As your spacecraft approaches the event horizon, your movements would appear slower and slower. The light reflecting from your ship would become increasingly red as its wavelength stretched under the influence of intense gravity. This effect is known as gravitational redshift. Eventually, your spacecraft would appear almost frozen at the edge of the black hole. Its signals would become weaker. Its light would fade. Then, it would slowly disappear into darkness. To the distant observer, it might seem as though you never actually crossed the event horizon at all. But from your perspective, you crossed it long ago. This difference between what you experience and what distant observers see is one of the strangest consequences of Einstein's theory of relativity. Both descriptions are mathematically correct. Neither observer is seeing the complete picture. Now the universe outside is disappearing behind you. There is no route back. No message can escape. No signal can warn anyone about what lies ahead. Only one journey remains, deeper into the black hole itself. And that's where the true danger finally begins. In the next part, we'll discover the terrifying force known as spaghettification and learn how gravity can literally stretch an object until every atom is pulled apart. Now that you've crossed the event horizon, there is no turning back. Your spacecraft continues falling deeper into the black hole, and at first, everything still feels surprisingly normal. The control panels are working, your oxygen system is stable, and from inside the cabin nothing seems dramatically different. But gravity is no longer acting the way you're used to. Near Earth, gravity pulls almost equally on every part of your body. Your head and your feet experience nearly the same gravitational force, which is why you don't notice any stretching. Inside a black hole, the changes completely. The closer one part of your body is to the center, the stronger gravity becomes. Even over a distance of just a few meters, the difference in gravitational pull can become enormous. Physicists call this a tidal force. Imagine your feet are slightly closer to the center of the black hole than your head. Gravity pulls on your feet much more strongly than on your head. At the same time, the sides of your body are squeezed inward while your length is stretched farther and farther apart. The effect grows stronger every second. At first, you might only notice a strange pressure. Then your body begins to stretch. Your spacecraft experiences the same fate. Metal bends, bolts snap, the structure twists under forces no material can survive forever. Scientists have given this horrifying process a surprisingly simple nickname: spaghettification. Because everything falling into the black hole is stretched into an incredibly long, thin shape, almost like a strand of spaghetti. If the black hole were relatively small, this stretching would become fatal even before you reach the event horizon. The tidal forces would tear apart your spacecraft long before you ever cross the point of no return. But around a supermassive black hole, like the ones found at the centers of galaxies, the situation is very different. Its event horizon is so enormous that the difference in gravity across your body is much smaller at first. You could actually cross the event horizon alive without realizing it. Only much later, as you fall deeper inside, would the tidal forces become overwhelming. This is one reason supermassive black holes are even more mysterious than smaller ones. They allow you to enter, before revealing their true power. By now, the outside universe has completely vanished. No light from distant stars can reach you in any meaningful way. Every direction points toward the same unavoidable future: the center. Somewhere ahead lies the most mysterious place predicted by modern physics. A place where our equations begin to fail. A place where density may become infinite, space may lose all meaning, and time itself could come to an end. Scientists call this mysterious destination the Singularity. But what exactly is a singularity? Is it truly an infinitely small point? Or is it simply a sign that our understanding of physics is incomplete? The deeper you fall into the black hole, the more reality begins to break away from everything you've ever known. Behind you, the universe is gone. No sunlight, no stars, no galaxies. Every possible path now leads only toward one destination: the mysterious center of the black hole. At first, your spacecraft continues falling smoothly. Surprisingly, you don't feel yourself being pulled downward because both you and your spacecraft are in free fall, just like astronauts orbiting Earth. Inside the cabin, objects seem almost weightless, but gravity has a hidden side. It's not just about how strong gravity is, it's about how quickly gravity changes from one point to another. Near Earth, this difference is tiny. Your head and your feet experience almost the same gravitational pull. Near a black hole, that difference grows rapidly. Your feet are slightly closer to the center than your head, so they are pulled with greater force. At the same time, gravity squeezes your body inward from the sides while stretching it from top to bottom. These powerful differences are known as tidal forces. At first, they are barely noticeable. Then, they slowly become impossible to ignore. The frame of your spacecraft begins to creak. Metal panels bend under enormous stress. Tiny cracks appear in places that were once perfectly solid. Every second, the stretching becomes stronger. Scientists have given this strange process a surprisingly ordinary name: spaghettification. Anything falling into the black hole is stretched into a long, thin shape, almost like a strand of spaghetti. For a small black hole, this process would begin long before you ever reach the event horizon. The tidal forces would destroy both you and your spacecraft almost instantly. But for a supermassive black hole, things are very different. Because its event horizon is so incredibly large, the change in gravity across your body is much smaller when you first cross it. You could pass the point of no return without feeling anything unusual. Only after falling much deeper would the tidal forces become overwhelming. This strange difference means that, in theory, a supermassive black hole gives you more time to witness the impossible. Yet no matter how massive the black hole is, the ending appears unavoidable. Every kilometer brings you closer to the greatest mystery in the universe. Somewhere ahead lies a place where Einstein's theory of general relativity predicts infinite density. A place where space may lose its meaning. A place where time itself could come to an end. Physicists call this destination the Singularity. But here's the problem. No scientist knows whether a true singularity actually exists. Our mathematical equations predict it. Nature may not. Many physicists believe that when gravity becomes unimaginably strong, Einstein's equations are no longer enough. At that point, another theory, one that combines gravity with quantum mechanics, must take over. And that theory doesn't exist yet. In other words, the closer we get to the center of a black hole, the less certain science becomes. The laws that explain galaxies, stars, planets, even the universe itself, may completely break down. So what really waits at the center? An infinitely small point? A bridge to another universe? Or something no human mind has ever imagined? The closer you move toward the center of the black hole, the less reliable our understanding of physics becomes. For everything you've seen so far, Einstein's theory of general relativity has been remarkably accurate. It explains how gravity bends space, why time slows down near massive objects, and even predicts the existence of black holes themselves. But now, Einstein's equations begin to fail. According to general relativity, all the matter that formed the black hole is crushed into an infinitely small point with infinite density, a singularity. The problem is that infinity usually signals something deeper. In physics, it often means our equations are incomplete. Think of it this way. Imagine trying to describe an entire ocean using only a glass of water. No matter how accurate your measurements are, they simply aren't enough to explain the whole picture. That's exactly what scientists believe is happening here. General relativity describes the universe on enormous scales: stars, galaxies, and black holes. Quantum mechanics, on the other hand, describes the incredibly tiny world of atoms and subatomic particles. Both theories have been tested countless times. Both are astonishingly accurate. Yet inside a black hole, they completely disagree. General relativity predicts a singularity. Quantum mechanics suggests that nature should prevent infinities from ever existing. Somewhere inside a black hole, these two greatest theories of modern physics collide, and no one knows which one is correct. This is why physicists have spent decades searching for something called quantum gravity, a theory that would unite Einstein's view of gravity with the strange rules of the quantum world. If such a theory exists, it could completely change our understanding of what lies inside a black hole. Some researchers believe matter never collapses into an infinitely small point at all. Instead, quantum effects may create an incredibly tiny but finite core, preventing true infinities from forming. Others suggest that space itself becomes grainy at unimaginably small distances, almost like the individual pixels on a digital screen. If that's true, then the singularity predicted by Einstein may simply never appear in reality. Even more fascinating is the possibility that the center of a black hole isn't an ending, but a beginning. Some theories propose that when matter reaches extreme densities, it could trigger the birth of an entirely new region of space-time. From our perspective, it looks like everything disappears forever. But from another perspective, a completely new universe could be forming. Right now, there is no experimental evidence proving this idea. It's one of the biggest unanswered questions in science. Black holes continue to challenge every law of physics we currently understand, and the deeper we investigate them, the more mysterious they become. But another puzzle is even stranger. If nothing can escape a black hole, then what happens to all the information carried by everything that falls inside? Does it disappear forever? Or is the universe somehow keeping a hidden record of everything? In the next part, we'll explore the famous black hole information paradox, a mystery so profound that it has challenged the greatest physicists for nearly 50 years. Imagine throwing a book into a black hole. The pages burn away. The cover disappears. Eventually, every atom that once formed the book falls beyond the event horizon. Now ask yourself a simple question. Where did the information describing that book go? Not the paper, not the ink, the information itself. In physics, information means every detail that defines an object. Its atoms, their positions, their energy, and the unique quantum properties that make it exactly what it is. According to quantum mechanics, information cannot simply vanish from the universe. It may change form, but it can never be completely destroyed. Black holes seem to break that rule. Anything crossing the event horizon appears to disappear forever. If that's true, then all the information carried by those objects is lost forever as well. That idea created one of the greatest crises in modern physics. It became known as the black hole information paradox. For years, scientists argued over this mystery. Then, in the 1970s, Stephen Hawking made a discovery that shocked the scientific world. Until then, black holes were believed to be eternal. Once formed, they would exist forever. But Hawking showed that this wasn't entirely true. Because of strange quantum effects occurring just outside the event horizon, black holes should slowly emit tiny amounts of energy. Today, we call this Hawking radiation. To understand how it works, imagine empty space. It isn't truly empty. According to quantum physics, tiny pairs of particles constantly appear and disappear everywhere in space. Normally, these particle pairs destroy each other almost instantly, leaving no trace behind. Near the event horizon, however, something different can happen. One particle falls into the black hole. The other escapes into space. To a distant observer, it looks as though the black hole has emitted a particle. Over an incredibly long time, this process causes the black hole to lose energy. Very slowly, it begins to shrink. For a black hole as massive as our Sun, this evaporation would take around 1067 years, far longer than the current age of the universe. Supermassive black holes would survive for even more unimaginable lengths of time. Eventually, according to Hawking's calculations, every black hole should completely evaporate. And that's where the paradox becomes even deeper. If the black hole disappears, what happens to all the information that fell inside? Did it vanish forever? If it did, quantum mechanics is wrong. If it didn't, then Hawking's original explanation must be incomplete. For decades, the world's greatest physicists searched for an answer. Some believe the information is secretly encoded within Hawking radiation itself. Others think it remains stored on the surface of the event horizon, almost like data written onto a two-dimensional cosmic screen. A few even suggest that the information escapes into another universe. No one knows which idea is correct. The debate continues today, but one thing is certain. Black holes are not simply giant cosmic vacuum cleaners. They may also hold the key to one of the deepest secrets in all of physics. For more than a century, black holes have challenged everything we thought we knew about the universe. The deeper we explored their mysteries, the more questions we discovered. Could a black hole hide a wormhole, a tunnel connecting two distant points in space and time? According to Einstein's equations, wormholes are mathematically possible. In theory, they could act as shortcuts across the universe, allowing someone to travel enormous distances almost instantly. It sounds incredible. But there is one major problem. Every calculation suggests that a wormhole would collapse almost immediately after forming. To keep it open, it would require an unknown substance called exotic matter, material with properties that have never been observed in the amounts needed. So while wormholes remain a fascinating possibility, there is currently no evidence that real black holes contain them. Another idea is even stranger. Some physicists have proposed the existence of white holes. A white hole is essentially the opposite of a black hole. Nothing can enter it, but matter and energy can only come out. Although white holes naturally appear in some mathematical solutions of Einstein's equations, astronomers have never found convincing evidence that they actually exist. Then there's perhaps the boldest theory of all. Some scientists suggest that every black hole could give birth to an entirely new universe. In this idea, matter doesn't simply disappear forever. Instead, after reaching unimaginable densities, it creates a new expanding space-time, completely disconnected from our own. If this were true, our own universe might even have begun inside a black hole belonging to another universe. It's an astonishing thought. But today, it remains speculation rather than established science. So after everything we've learned, what is the most likely answer? The honest truth is, no one knows. Scientists are confident that black holes exist. We've photographed their shadows. We've detected gravitational waves from their collisions. We've watched stars orbit invisible supermassive black holes at the centers of galaxies. But what lies beyond the event horizon remains hidden. Perhaps the singularity is real. Perhaps quantum gravity prevents it from ever forming. Perhaps information is preserved in ways we don't yet understand. Or perhaps nature is waiting for us to discover an entirely new set of physical laws. Every generation of scientists has uncovered mysteries that once seemed impossible to solve. Black holes may simply be the next great frontier. They remind us that even with all our technology, the universe still holds secrets beyond our imagination. And maybe that's what makes them so fascinating. Not because we know what's inside them, but because we don't. If you enjoyed this journey into one of the greatest mysteries in the cosmos, don't forget to like this video, subscribe to the channel, and turn on notifications for more cinematic space documentaries. Until next time, keep looking up, keep asking questions, and never stop exploring the universe.